All right, so now let's talk about the principle of D'Alembert. Okay, so this basically tells you something about this idea of forces of constraint. Okay, so the constraint force acts along the normal direction to the constrained surface. All right. So if your constrained surface happens to be the zero level set of some function, let's say g of q is 0, right? Then what happens, if you will, is that the gradient of that function, right, gradient of g, if you will, is then going to be pointing in a direction which is perpendicular to this zero level set. Okay, and so if you have a sort of particle, it's like which is constrained to be on the surface, if you will, then the force of constraint, let's denote that f sub g, right, is equal to some sort of parameter lambda, well, not parameter, but it's like some appropriate, it's like a multiplier, if you will, times the gradient of g at q. Okay. All right. So yeah. So again, that's to say that it is in the direction of the gradient of the constraint function. G at the point of contact. Okay, so if we denote the force of constraint by Fg, right, then you have that Fg is parallel to the gradient of g at the point of contact q, right? Or if you prefer, it's like with an appropriate sort of scalar factor lambda, right? Fg is equal to lambda gradient of g q, which is what I drew over there, where lambda is sort of a scalar. All right, so what you can do then is that you can use this observation to write down then the equations of motion for say a particle, it's like which is then constrained, it's like to move or constrained to stay, it's like on this constrained surface. Okay, so using Newton's second law, right, the equations of motion have the form so mv dot is equal to negative the gradient of the potential plus lambda the gradient of the constraint. Okay, and then q dot is equal to v. All right, so those, but of course you don't have enough to close the equation yet. You still need to know what lambda is. And then the third constraint, if you will, is that g of q is equal to 0. So what you oftentimes find then is that this constraint, it's like is enough to then allow you to solve with the lambda, which guarantees that you can actually use this system of differential equations with an algebraic constraint, it's like to evolve the situation forward. So this is an example of what is called a differential algebraic equation. And there are sort of methods it's like developed. It's like for the solution of general differential algebraic equations, and there it's like there's this idea of the index of a differential algebraic equation, which more or less has to do with the question of how many times potentially you have to differentiate the algebraic constraint and then substitute it into differential equation to then get a differential equation which does not essentially involve the multipliers. Okay. So how many times do you have to differentiate? It's like the algebraic constraint. It's like to get a closed sort of system of differential equations. Okay. All right, and in practice, it's like the higher the index of a differential algebraic equation, the harder it is to develop good numerical methods for it. Okay. Anyway, so all right, so this is a differential algebraic equation, and the parameter lambda, right, is an unknown. Right, which is uniquely determined by the condition that q as a function of time lives on the constraint surface. So that basically means that g evaluated of q of t is equal to 0. And so if you imagine differentiating this, then you would get derivatives of q as well, which you can then, it's like use the differential equations to try to then eliminate the lambda in principle. Okay. So, so let's see what happens in this specific case. All right. All right, so let's differentiate g of t. So that's d dt of g q of t, right? So this is, of course, so let's just apply the chain rule. So the gradient of g at q of t times q dot, right? And so I can write this as the gradient of g q dot v, and this is equal to 0. So here I substituted, it's like one of the differential equations. All right, and then I can differentiate this one time more. All right, maybe I should try to copy this to the side, right? So you have mv dot is equal to minus gradient v plus lambda gradient gq. Q dot is equal to v, and then g of q is equal to 0. All right. Okay, so I can differentiate this once more. So d squared dt squared of g of q is equal to v paired with g qq, right? So this is like a quadratic form. It's like with a mass matrix which is related to the Hessian of this g function. right, plus M inverse this multiplied by minus the gradient VQ plus lambda. Okay, is equal to 0. And so what should be clear, of course, is that here it's like you've taken advantage of the expression for v dot, if you will, right? So v dot is just M inverse times this thing, which is what we have here, right? Because when you differentiate this, this is essentially a product. You apply the product rule. You have to differentiate this piece, right, which gives you this first term here, or you can differentiate the second piece, which gives you this gradient of g term times v dot. So the gradient of g term times v dot, but where I used the first differential equation to write v dot as M inverse multiplied to this term here. All right, so that's basically what I've done here. Is to just apply the product rule to this and then substitute the expression for v dot into the expression here. Okay, so you have this, and so where GQQ is the Hessian, of G, all right? And so if this gradient is not 0, right? So if the gradient of this is not 0, right? We can solve basically for lambda, if you will, right? We have that lambda, right? So you have some complicated expression, but the bottom line is that you have some complicated expression which involves a lambda being equal to 0, so you can solve for the lambda as long as this is not 0. So if that happens, you can solve for the lambda to give me M over the norm of the gradient of G multiplied into 1 over M minus this inner product with the Hessian. Okay. All right. So anyway, so you can solve for this lambda. It's like now in terms of things which you know, and plug it into this, and then these two equations at the top without the last equation, then is a closed differential equation, right? All right, so that was for a fairly general, it's like sort of mechanical system. So let's specialize this to the n-body problem. Okay. So now let's consider the n-body problem. With M holonomic constraints. Okay. All right. So you have Q dot is equal to V. M V dot is equal to negative gradient of the potential minus now with a bunch of multipliers, lambda I of, okay, lambda I going from I equals 1 to M because the M holonomic constraints multiplied into the gradient of these constraint functions. Okay. And then you have the condition that Q is on the constraint surfaces for all M of them. Okay. So you have this n-body problem then with these M holonomic constraints. Okay, so here big M is a positive definite symmetric matrix. and then you typically assume that the gradients of the holonomic constraints form a linearly independent set, right? So we typically assume which of course this gradient Q gi of Q term, right, form a linearly independent set. Okay, and this is more or less saying that every time you have one of these constraints, it's like you go down in dimension. It's like in terms of the constraint surface, right? So if you have say a vector space of dimension d working in RD, and then you have m of these constraints, then locally the dimension of this constraint surface should be d minus m, right? So otherwise known as a codimension m surface or manifold, right? All right. Okay, so if you have that, you can talk about the idea of a configuration manifold. So okay, it's denoted by script m as the space of admissible positions. Subject to the position constraints. So M basically is the set of points Q in RD with the property that GI evaluated at Q equals to 0 for I equals to 1 to M. Okay. All right, so that's the constraint manifold, or the configuration manifold, all right? And then what we need, amongst other things, is to look at tangent spaces to this. So let's compute Tm. Okay, so let's say that Q bar be a point. Erase the rest of this. Okay, so let Q bar be a point on the configuration manifold. Okay, and what we're going to do, if you will, is that we're going to think of the tangent spaces as being described in terms of parametrized curves on this configuration manifold, and then differentiating, looking at tangents to these parametrized curves, right? So this is how we're going to end up computing Tm, if you will. And then we consider the set of all parametrized curves containing Q bar. All right, so if you will, it's like if you have a picture like this, you have a point Q bar, and you look at the curves which contain Q bar as one of the points, okay? And then essentially the idea is that, if you differentiate one of these parametrized curves at the point Q bar, with the property that the curve is on this configuration manifold M, then you have an element of the tangent space. It's like 2M, right? And you vary over this to then find all possible tangent vectors, if you will. Okay, containing Q bar, and I should say, and lying in this configuration manifold M. Okay, so you want to look at each parameterized curve. Let's say Q of t with the property that Q at 0 is Q bar, right? So it's natural to consider parameterizations where Q at 0 is Q bar, and then V bar is Q dot at 0. Okay, so that's the setup. So what you do, of course, is you look at this constraint, and you want this again to be true. It's like for Q or for all t, right? So since gi Q of t equals to 0 for all t, right? You can differentiate that, and that has to be 0. The time derivative of this has to be 0. So d dt of gi Q of t, that has to be 0. All right, so but this is equal to the gradient of gi evaluated at qt dot q dot of t. Okay, or if you prefer, it's like I can write the q dot as v of t. And that has to be 0. Okay, so that's telling you, if you will, that the tangent vectors are perpendicular. It's like to the gradient of the constraint function, right? And that's perhaps not so surprising because, as we saw before, the gradients of the constraint functions, right? The gradients of the constraint functions are normal to the constraint surface, right? So what this is basically saying that if you want the tangent to that, then you have to be perpendicular to the gradient of the constraint function. So that's what you might expect. Okay, so yeah, so this implies that the gradient of gi at q, right, q bar, inner product with, well, dot product with v bar is equal to 0. Okay, so the set of all possible velocity vectors at the point q bar, right, is a linear vector space called the tangent space at q bar. Okay, and it's denoted by the following. So I write this as t q bar, so that tells me the base point of M, okay? And this is the set of v bar in Rd with the property that the gradient of gi at q bar, right, dotted with v bar is equal to 0 for I is equal to 1 to M. Okay, so it has to be normal to all the gradients, it's like of all the constraint functions. Okay, so that's the tangent space, and then you can sort of look at the disjoint union, it's like of all the tangent spaces at different points in the manifold to give you what is called the tangent bundle, right? Then the tangent bundle of M, right, is the set of QV, right, with Q, which is in M, and then V is in the tangent space at Q of M, and the tangent bundle is denoted Tm. Okay. All right. So you can write this. It's like a little bit more compactly. It's like, by instead of looking at scalar valued functions g sub I, you can look at a vector valued function, big G, if you will. Well, little g, it's like which contains, it's like all these scalar valued functions. Okay. So we can rewrite the equations more compactly. By introducing the vector function let's see, g of q, which is g1 of q all the way up to g m of q transpose, and then we can look at the Jacobian matrix associated with this. So we denote its Jacobian matrix by the following. So let's say big G of Q is Jacobian of this vector valued function, or equivalently that G of Q transpose is the gradient of this vector valued function. Okay, and then the same way that you put all the constraint functions together, you can put all the constraint, all the multipliers together as well. All right, and then you let lambda be the M vector of multipliers. Okay, so lambda is lambda 1 to lambda M, whole thing transposed. And with that notation, then you can write things much more simply. So then the equations become Q dot is equal to V, right? V dot is equal to negative the gradient of the potential, right, which is sort of the Newton's law part, minus GQ transpose lambda, and then you have G of Q is equal to 0, but it's really a vectored 0, right? So it's a 0 vector. Okay. All right. So that allows you to write down the equations a little bit more compactly. And then the same idea is that, which was true as before, is that you can then differentiate this constraint an appropriate number of times to get rid of the multiplier. So we can eliminate the multiplier. So that multiplies lambda I by differentiating velocity constraint. Okay, so the velocity constraints were that, again, the GIs, the gradient of the GIs are perpendicular, it's like to the velocity vectors. Okay. All right, so this is coming, if you will, it's like from our discussion of tangent bundles and tangent spaces. Okay. Okay, which yields the following. So Q dot is equal to V again. M V dot is equal to minus gradient of V, right, minus GQ transpose some lambda of Q and V, right? So the multipliers, if you recall, it's like depend on Q and V, and where the multiplier looks like the following: minus G M inverse G transpose inverse multiplied into Gm inverse the gradient of the potential plus GQQ acting on the inner product of V with itself. Okay. Right, so where G is just G at Q, and this GQQ VV term, right, is an M vector. Okay, with the property that GI QQ VV. Well, maybe I should write it as this way. So this thing, the ith term, right, is equal to the sum over K and L of the partial, second partials, right? So this is the Hessian term. Okay, and then you I think the right, so maybe I should write this as a bracket instead. Okay, so what you have basically is that you have this Hessian term is going to be thought of as a quadratic form, which takes two vectors, right? So you have this matrix, right, which you can think of as being something like V transpose times this matrix times V, if you will, right? So that's a quadratic form, and that's basically what you have there. Okay, anyhow. Okay. Yes. Okay, I should say that it's really the quadratic form. It's like associated with each of the Hessians of each of the GIs. It's like contracted, right? Okay. All right. So anyway, so the so this expression for the multipliers is well defined. If this matrix is invertible, on the constraint set M, which is always true if GQ has full rank. Which is of course equivalent to the condition we talked about before, which is that the gradient of the GIs, it's like form a linearly independent set. Right. So, i.e. the set of gradients of GI, right, is linearly independent. Okay, and M is positive. Well, this mass matrix M, not the constraint manifold, is positive definite. Okay. All right, so let me just stop here for now. Then we'll show some examples, and then we'll talk about some numerical methods for addressing these kind of constraint systems.